Hi everyone, welcome to another video for research design and analysis. This is going to be our final video in the series on the t-statistic, where we're going to be talking about how we can use these t-statistics to calculate confidence intervals. And we'll talk about this in both directions. So if we can find the confidence interval, then we know kind of what sample means to expect if we know the population mean, but we can also work in the reverse direction. And if we know a sample mean, we can construct a confidence interval to get some assessments of compatible values of the true population parameter. So first off, let's work with a little analogy, because these confidence intervals can be a little bit hard to understand mathematically. But let's say, I'm a world famous archer, and I'm saying I can shoot an apple off the top of your son's head. And I'm going to say most of the time I hit the apple, but 95% of the time my arrows fall in this region. Now, if I aim for that point, right, 95% of my shots fall in this region. Maybe a lot of the time I still hit the apple, but it's not unusual to miss below to a certain degree or above to a certain degree. And the big question is, do you let your son sign up for this? Probably not, right? But what if I told you, look, I actually have gotten better, and now 95% of my shots, fall in this region. Well, that looks better, but there's still a pretty decent probability that your son takes an arrow to the head, so you probably don't let your son sign up. And now I can say, look, no, I've gotten even better. So, if I aim for this point, 95% of my shots are going to fall in this region. So I almost never hit children in the head. Now, those still aren't great odds if we're actually talking about shooting arrows at, apples balanced on children's heads. But this is setting up an analogy to the idea of sampling variability and what sort of things we might expect in our samples relative to the parameters in the population. So if we think about the point I'm aiming for as the true population mean, and this confidence interval as where 95% of sample means are going to fall, right? We can say if we know this, we can know how far away from that population mean these samples will tend to fall. Now, they certainly might fall outside of that range sometimes, right? But most of the time they will fall in that range. And then the question is, how much uncertainty are we willing to accept given the kind of costs of the situation, right? So in this situation, the costs are very, very high. So even this pretty good confidence interval, we might not be entirely comfortable with. Okay, so again, right, remember we're talking about sample means rather than arrows, of course, but this is just kind of a motivating analogy that I hope is a little bit fun, right? But the idea is if this point is the true population mean, mu, then we can say the 95% confidence interval represents some upper limit and lower limit in the sampling distribution, right? So again, the distribution of sample means under the central limit theorem is always going to follow an approximately normal distribution, and it's going to get more and more normal as the sample size increases. But we can actually, for a sample of a given size, really draw specific limits. And specifically, we can say that the upper limit of this 95% confidence interval would be equal to the population mean under the null hypothesis, plus the critical t-value for our alpha level divided by 2, right? So oftentimes we'll set alpha equal to 0.05. So we're looking at the critical t-value that separates the extreme 5% of the data from the middle 95% of the data. So this critical t-value, right, it's a little bit confusing at first, but it's alpha divided by 2 because I have 2.5% in this tail and 2.5% in this tail. So if I'm thinking about this in just one direction, it's the t-value that separates the 2.5% in the tail from the middle of the distribution. So that's why it's alpha divided by 2 for this kind of two-tailed example where we're constructing the confidence interval. And then we're going to multiply that t-value by the standard error, because if you remember from our example with the normal distribution when we were talking about confidence intervals, this t-statistic is in units of standard error. So if I actually want to get an upper limit that is in the same units as the population mean, I have to multiply it by the standard error, and then that will give me the margin of error, right? The difference between the population mean and the upper limit. And by adding that value back onto the mean, it will then give me the exact cutoff, the score, right? I should say the value that corresponds to the 97.5 percentile of sample means. Similarly, I can get the lower limit in the same way, right? I'm going to take the mean of the population. I'm going to subtract now, rather than add, the critical t-value times the standard error. So I'm transforming this critical t-value back into the original units, subtracting it from the mean, and that's going to give me the lower limit. It's going to give me the value that separates the bottom 2.5 percentile of the sampling distribution. And these formulas, just in case they don't look familiar, right, they are structurally exactly what we did with the normal distribution. The only difference is that we're using t-values rather than z-values, but we can derive them right from the actual formula for t observed, where if we're rearranging these to solve for a particular x, right, the upper limit is just a particular x bar value. It's a particular value of sample means. So this is just an algebraic rearrangement of this equation where we're solving for a particular x bar, and the same thing for the lower limit. And of course, the difference is that in one case, we're adding the critical t-value to get the upper limit and subtracting off the critical t-value to get the lower limit. So now, why is this important? Well, right, if we know mu and sigma, then we can define where most of the sample means are going to fall, like in the example I just gave you, right? If we know what the true population mean is, then we can say that, for a given degree of confidence, we know where samples of a particular size are going to land. So we could say we want a 95% confidence interval, or we want a 99% confidence interval, or we want an 80% confidence interval, right? There are lots of different confidence intervals we could potentially calculate, but the underlying formula would be the same. It's just going to change what particular value of, or what particular t critical value we plug in here. But the idea would be is if we know mu, we can draw those confidence limits, and then if we repeatedly sampled from the population, we would see our distribution of sample means follows a nice t-distribution like this, with most of the sample means following around the population mean, but they will vary and spread out. But if this is a 95% confidence interval, then 95% of them will fall within that confidence interval. Now, where these come in really handy is when we don't know mu and sigma, which we usually don't. So we want to work backwards from the statistics in the sample in order to try to estimate the parameters in the population, right? So here we knew mu, and we could say, well, this is where we think the sample means, the x bars, are going to fall. Here we know x bar, but we don't know what mu is. However, we can use the same equation now working backwards to get upper and lower confidence limits that will give us plausible values of the population parameter mu. So we would take our x bar, and to get the lower limit, we would subtract off the standard error times the t critical value. And to get the upper limit, we would add the standard error times the t critical value. And that would give me some limits that then say what plausible values of mu might have led to this x bar that we observed. Now, we can't say which mu did, right? Because this mu would be a plausible value that could have led to that x bar, and this mu would have been a plausible value that could have led to that x bar. However, extreme values of mu would be unlikely given the data that we observed in the sample. And we can see this a little more clearly if we think about the sampling distribution of means and the mu kind of being fixed at either end of this confidence interval. So the upper and lower limits of the confidence interval represent the most extreme population means, right? That is to say the mu's that are compatible with the sample mean, the x bar, that we observed in the sample, out to the given level of confidence that we specified, right? So you can think about it this way. If I have my x bar, I calculate the lower limit of my 95% confidence interval, and I calculate the upper limit of my 95% confidence interval. That lower limit represents the smallest value of mu that would have plausibly generated a sampling distribution that contains x at that 95th percentile. And the upper limit represents the largest value of mu that would have plausibly generated a sampling distribution that contains x at the lower limit of its 95% confidence interval. So any value of mu in between those two is possible, and we can't really rule those out. But we can say that values of mu that are higher than that are less likely, because they are their sampling distributions, you can imagine being shifted over here, they are less likely to have generated this x bar due to sampling variability alone. Similarly, extremely low values of mu are less likely, because you can imagine their sampling distribution over here they would have been less likely to generate this sample mean due to sampling variability alone. So by getting that confidence interval, we get an estimate of what mu might be in the population. Now, we need to be careful in our interpretation of this confidence interval, however, because the frequentist confidence interval has a slightly tricky interpretation, right? Sort of strictly speaking, what this confidence interval means is that in the long run, 95% of confidence intervals drawn to these limits will contain the population mean. But that does not mean that ours necessarily does, right? All values in that interval are, compatible estimates of mu that could have produced x. Or could have produced x bar, I should say. So that's why I actually sometimes like to think about this really as more of a compatibility interval than a confidence interval, because it's telling you what the lowest value of mu that's compatible with what you observed and what the highest value of mu that's compatible with what you observed might be. So I think this visualization and thinking about that as a compatibility interval is helpful. But the thing we definitely want to avoid is feeling like we are 95% confident the true mean lies in any given interval. Now, again, this contradicts the frequentist definition up here, right? Where we're not saying that it's 95% confident that it lies in the interval. We're saying that 95% of intervals will contain the true mean. And those are subtly different, but importantly different statements, right? Because if we wanted to say we were 95% confident that the true mean lies inside a particular interval, that's again going to require Bayesian statistics with have more specific model assumptions. And you can refer back to our video on p-values, because this is tied up in a similar misinterpretation of the p-value, right? In the same way that for our p-value, we're getting the probability of a sample statistic as extreme or more extreme than the one we observed, assuming the null hypothesis is true. That is not the same as getting the probability that a hypothesis is true given the statistic that we observed, right? And this logic for p-values is the same for confidence intervals. If we're assuming that the null hypothesis is true, right, we're looking at the probability of our data given the hypothesis. And with our confidence interval, we cannot then say, well, what's the probability that the hypothesis, right, or the hypothesized true mean lies within our confidence interval given the data. In order to get this posterior probability, again, that's a very valid question, but it's going to require slightly different methods that we'll hopefully cover in some future sections.